Hey everyone, welcome to tutorial number 6. Congratulations on finishing week 7. I hope that you are doing well, and I hope that you're having a happy Halloween. Just a few warnings, a few things to get you up to date. Assignment 7 is due on November 2nd. The second midterm is on the 6th. It's in red because it's super important. You don't want to miss this one. Assignment number 8 is due on the 9th. That's a few weeks out, but it's not too early to start assignment number 8. We have 4 topics to cover today. One is Big O. We're going to do a little bit of a recap. I apologize that this isn't a true orange for Halloween. The yellow and black color scheme was the best I could do. We're going to go over contracts, order, and sorting. And by order, I mean total order and not order notation, because this Big O notation is an order notation, and you talk about a few other order notations. So here's the definition, if you remember. F is of order G if there exists a C greater than 0 and an X naught, or X0, pronounced X naught, such that for all X greater than that X naught, F is less than or equal to G of X. So what does this mean? It means that for suitable constants, F is smaller than G. This means that after some point, if you look at the graphs, if you want a visual interpretation, at some point, F is always smaller than G, and we're also allowed to scale G by a constant. So this means that I can take G and I can make it really, really big, and then see if F is below G. And if this never happens, F is not order G. If we can bound F by some constant multiple of G, then we say that F is of order G. And this is a way of showing that F is F does not grow faster than G in the long run, is what we're trying to measure by this Big O notation. A quick recap on how to prove something is of order G is that you need to provide constant C and X naught to satisfy the above definition. To show that something is not of order G, you need to show that for every possible value of C, F is never going to be completely under G. So that is, for any scalar C, F always will overtake G in the long run. And the idea of this disproof is that for any C, you actually provide an X that is greater than any X naught. So for any C and X naught, you give them an X. And these two proofs are essentially what you were doing on A6 with find X and then the providing of a suitable C and X naught to make it say impossible. And the way A6 was written is that this inequality was reversed. It was the negation. And that's why impossible meant order F and G. Now, here's something interesting to note, is that X is of order X. It's also of order X squared, and it's also of order X log X. So this is basically me saying that be careful, because it doesn't mean that this is actually how it runs if something has runtime of X squared. This just means that we've been able to bound the steps by X. For examples, of course, A6, you've done examples and you've seen examples in lecture and in the preamble of A6. I'm going to show you right now an alternative method that doesn't involve any inequalities. It's not always as readily applicable, but you should know it. By that, I mean it's probably not necessary to memorize doing this for your midterm, but I think you should know it as a student of computer science. So let's show that X squared is of order 1 over 10 times X squared plus 1 over 20X plus 1 over 10. And now obviously you say, wait. Why can't I just take, say, X equals 20 and then bound it? And I'll say, yeah, that's fine. That's perfectly fine. But that's your intuition, and I'm going to show you a way of making that intuition formal using some of the identities. So the order of F plus G is just the order of whichever one is bigger, the big O. And in this case, we can take F to be 1 over 10x squared plus 1 over 10, and G to be this middle term, 1 over 20x. And the X squared is the larger order of the two, so we can move to this step. It's the same big O as this, and then you see that this is just two constants, one added and one multiplied. So we have this other rule, that O of A times F plus B is just O of F. So we can conclude that this order is actually just order of X squared. And then obviously X squared is of order X squared. You can check that by using C and 1 in the definition, so I lied a little bit. You do have to use some equalities, but they're very easy inequalities, sorry, not equalities. It's x squared is always less than or equal to x squared. Question again, could we have just used the definition with suitable c and x naught? Of course, you always can. It's the definition. We would have to deal with more inequalities, and you would have to just do the trimming of the inequality like you usually do. The next topic that we're going to look at is contracts. Who has seen this error? Hands up. A lot of you. That's great. So function contract violation expected something given something else is what Dr. Racket will tell you, very convenient of it, when you have given information to a function that it does not want. I'll give you guys a little better view of these slides, and we're going to explore what exactly causes this error and how we can get around it. I talked about it briefly in a previous tutorial, but now we're going to talk about it in a more rigorous sense. I believe that Rivers has talked about contracts before in his formatting video, but we're going to do a bit of a recap on that right here. So in math, functions have a domain and range. In a casual sense, the domain is just the set of input values and the range is the set of possible output values. In practice, we usually talk about the range as if it were the codomain, which is kind of a generalized range. In this course, we discuss functions or procedures in Racket. I just said these two are pretty much the same in Racket. The procedure is the predicate for functions, or the data specification for functions. A function contract is simply a specification of the domain and range. So I apologize for just reading this slide verbatim mostly, but a contract is just a fancy way of saying, well, what is the domain and what is the range? What's the input? What's the output? We're going to look at a few examples right now. Here is a screenshot from the Racket documentation. It says full del proc init list ... plus arrow any c. And then it says proc procedure init any c list This is a contract. This is exactly what we were talking about. Here's your function full del. Here is the domain or the specified input, and then here is the output or the range. So the domain requires one procedure, one initial value, and one or more lists. That's the ... one or more lists. So these are the specifications for the data. So this is proc is a procedure, and it is an any, and LST is a list. For sum2, our contract would be nat to nat. I said could be and not is nat to nat because you could also write sum2 so that it accepts any integer, not necessarily positive, and by nat I mean a natural number. The contract for square could be num to num. Notice that it's real numbers to real numbers. If you wanted to be a bit more judicious with your domain, you could specify that it would be greater than or equal to 0. A contract for cons would be any and list going to list. So this means that the first element of the cons is the item that you're putting into your list, and then the list is the rest of the list. A very interesting point here is that we might want to only deal with contracts that go from one thing to one more thing, and not contracts that have two or more things and output two or more things. We can always modify a multiple input function to be a single input function. The method we use is called currying after Haskell curry. And here is a simple example. The principle is that we're going to take our function and something like cons that has multiple inputs, and instead of accepting two things and outputting one thing, we're going to accept one thing and then output a function. And that function is going to keep accepting more things until we've accepted all the parameters we need and we can compute the result. So in this example, it's define new cons first. So my new cons is going to accept the first element of the list. So that was any here. And then it outputs a lambda. This is lambda of rest, and then it conses the first to the rest. So instead of cons taking in two values and outputting a list, I'm going to take in the first value, I'm going to output a function, And then if you put the rest of the list into the function, it's going to build you cons. So new cons has the following contract, any, and then as an output, it gives you another function. So this other function will consume a list and output a list. Now let's talk about total order. Try to remember what the definition is. I paused it for a minute so that you could read these, and you will have noticed that I didn't actually put the specifications on the elements X and Y in the set. I just said reflexive property, antisymmetric property, transitive, and the total order, or the total property. And I would like to see if you can remember what each of these means by yourself. You should have them memorized, if not the name, at least the statement of them. I'll try to think of those right now, and if you want to pause the video, because I'm about to say what they all mean and spoil them a bit. So the reflexive property for a total order is that any element compared to itself outputs true. So X is less than or equal to X always is true. The antisymmetric property is that if we have two elements X and Y, and X is less than or equal to Y, and Y is less than or equal to X, then X and Y are equal. The transitive property is that if we have three elements, A, B, and C, A is less than B, and B is less than C, then A is less than C. And these are just the three basic things that if you were trying to generalize the less than or equal to symbol, you would like your new function, your new comparison function, to have these three properties so that you can do the kind of things that you expect of it. One of those things might be sorting. The total property means that we can compare every two elements. Sometimes you can't compare every two elements in your domain of things that you would like to compare. For example, if you want to compare sets, comparing by subset is a partial order, but it's not a total order because you can't compare every two elements. For example, you can't say whether the set containing 1 and 2 is a subset or not of the set containing 3 and 4, or vice versa. You can't compare those sets with respect to subset. Note the similarities and to the definitions of partial orders and equivalence relations. So we didn't really talk about them in this course. They were both mentioned briefly, I believe, but a partial order is very similar to a total order, except it lacks the total property. You can't compare every two things. The equivalence relation, like a total order, is a generalization of something else. So the total order is the generalization of the less than or equal to sign, where the equivalence relation is the generalization of the equal sign. So comparing two things to see if they're the same is the equivalence relation, and comparing one thing to see if it's smaller than another thing is the total order. Next, we can talk about total orders with respect to data structures that we've already created. So we might want to put something other than numbers into an AVL tree, such as on assignment 7, when we give you AVLCS.racket, we might have this first instinct when we read the question to put our cards directly into the AVL tree and then look at the AVL tree. We can call size in constant time. So we'll know that after we have filled up our AVL tree to the correct size, that we can solve the problem and give back all the cards in our tree. Unfortunately, AVLCS145 only works for numbers, so we have to abandon this approach. We need to only put numbers in it and keep the AVL tree and the cards separate. Here's an idea though. What if we defined a total order that could be put into the BST? I believe Professor Cormack showed an example of this in lecture. And how we could alleviate this problem is something that you'll see on assignment 9, where we build a data structure and all the operations. It's an ordered set data structure. It's very similar to the implementation that you saw on assignment 6, problem F. And what we do is that we give you the total order and we say, we need you to build these things for the total order. And they're things that you would expect. What is the comparison operator? What does the data structure look like? How do you build one? How do you unbuild one? And then also a membership predicate, and then some kind of associative operation, which is a bit of a bonus, doesn't necessarily have to do with total order, the associative operation. But to fix this problem of I can't put cards into an AVL tree, we change our AVL tree to accept anything but we need to provide what the comparison operator is. So that was kind of a long-winded way of going about saying that we modify our structure definition so that we can put a larger variety of things into it. The fourth topic is sorting. The question at hand is we have a set of data, grades, names, phone book. We want to sort it. We want to put it in order from greatest to least based on some metric, some total order that we've defined. Well, let's take a look at selection sort and go over the key points of a sorting algorithm. So the strategy with selection sort is that we're going to move numbers into a new list by selecting the largest from the old list each time. The invariant, which is kind of similar to a contract, is something that we expect to always be obeyed at each step of the algorithm. All elements in the new list are greater than or equal to all of the elements in the old list. The second list must be sorted, and the elements in both lists are exactly the elements of the original list. So with that invariant, you can immediately see that if we can find a way to move everything from the old list into the new list will be our old list, but sorted. Wouldn't that be great? The thing that's not so great is that the worst case running time is n squared, O(n) squared, where n is the length of the list. And this will happen when you have to look through the entire list to find the largest element each time. So whatever method you use to find the largest has to go and take as long as possible. Here's an example where we sort a list of numbers using our very common less than total ordering. So here's 2, 1, and 3, and empty set. These are our first list, our old list, and our new list. We're going to take out the largest element, put it into our new list, then take out the largest element from this list and put it into our new list, and finally take the largest element of this list and put it into our new list. At this point, you can see that the first list is empty. Then you look at your invariant, you say, wait, but the union of the first list and the second list is the original list, and if the first list is empty, that means that everything's in the second list, and the second list is sorted, so that's great. And then you look at this list and you say, yep, that's my sorted data, 1, 2, 3, awesome. The next slide is going to be about stable sorting, and I'm introducing it before I show you the slide because it's kind of a heavier topic and the slide has a lot of text on it. The idea with stable sorting is that an unstable algorithm will sort and output the sorted data, but it won't preserve the order that they're in relative to each other when they're equal by the sorting comparator or the sorting operation. And the idea is that you might have some other data attached to it as well. So for a simple example, if you wanted to sort everyone in your class by height and by name, you could first sort them alphabetically by name and then sort them by height. An unstable algorithm would output all of these people and they'd be sorted by height, but they might not necessarily be sorted by name for the same height. For example, all the people that are 6 feet tall might not be in alphabetical order anymore. A stable algorithm, on the other hand, would sort them by height and it would preserve the original order by name. So all of the people who are 6 feet tall would still be in alphabetical order. Here's an example. So stable sorting algorithm definition preserves the relative order of equivalent elements. They're not equal elements because they might have other fields that are irrelevant. As in the example, when we sort people by height, their name is irrelevant. For example, if we want to compare fruits and prices, this is a student example. I won't name them because I didn't ask them to use their example, but it's a fabulous example, so I'm using it here. What if I just have this random list of fruits and prices? An apple is worth $1, a pineapple is worth $5, a banana worth $2, an orange worth $2 as well, a guava only $1, and the mango being worth $3. We can sort this by price, and an unstable sort would look something like this: guava, apple, orange, banana, mango, pineapple. But if you've noticed, in our original list, apple was before guava, and banana was before orange. These are not in alphabetical order themselves, but apple, guava, and banana, orange are relatively in alphabetical order. And now you'll see that the alphabetical order was not preserved. Their original order in the original list wasn't preserved. But with a stable sort, apple comes before guava and banana before orange. And a selection sort can be unstable depending on the implementation. You might be asking, why do I want a stable sort and not just a regular sort? The stable sort is a little bit more useful to us for a few reasons. And the first one is that if we have them in some kind of queue, some kind of priority, we will keep that priority. And the second reason, which is kind of the same as the first if you really think hard about it, is that we can sort back to back, sort based on height, based on age, based on name, based on phone number. And then in each of the subcategories, our data will still be sorted. So if you wanted to sort by multiple criterion, it's only possible with stable sorting algorithms. As always, here are some practice problems for you. We've got 3 of them so far, one concerning order notation, another concerning total order, and a little bit of practice with order notation, and then a stable sorting algorithm problem for you to think about stable sorting and sorting in general, and it is selection sort. Again, thanks for watching. Have a great Halloween, and I hope to see you sometime soon. All of your classmates are wonderful people. We have a lot of people who are saying that they want more friends. Rivers and I would be happy to be your friend, but of course, you probably want friends that are students as well, so that you can study together and talk about the woes of being in CS 145 and the associated first year math courses. All of the people in this class I've met are super nice. They're super friendly. So if you reach out to any of them on Piazza or MS Teams or email even, I'm sure they would get back to you and be super happy. So have a great weekend. Have fun studying for the midterm, and I hope to see you sometime soon. Bye.